Hi. Today we're going to do our very last movie of the semester. So we're going to look at a sample thermodynamics problem. We actually have two goals today. First we'll talk a little bit about heat capacity for an ideal gas. And then we'll go through our example problem. Okay, so heat capacity. So we remember that when we did solids and liquids, and also a little bit of gases, actually you can apply this a little bit. Our equation for the amount of heat, Q, necessary to raise the material's temperature by an amount delta T is mc delta T. M is the mass of the material. And this constant C is known as the specific heat, and that depends on the material. For gases, generally we use a similar equation. We have an amount of heat Q. Again, delta T is in there. Instead of a mass representing how much stuff we have, we use the number of moles, which is N. And then instead of lowercase c, we have uppercase C, which is the heat capacity. And we have different types of heat capacities depending on what the process is. So we'll do this for a monatomic ideal gas and see what happens. And we'll pick a particular process. We'll do the constant volume process. So here we have the heat capacity at constant volume, C with a V subscript. That's the heat capacity at constant volume. So Q is NCV delta T actually applies for any type of ideal gas, monatomic, diatomic, polyatomic, whatever you want. For a monatomic ideal gas, we actually showed previously that the amount of heat is 3/2 nR delta T. Okay, so in this case we compare NCV delta T to N 3/2 R delta T, and we find that the heat capacity at constant volume for a monatomic ideal gas is 3/2 R. So if you go back and think about what we did for solids and liquids, we have a constant, the specific heat, that depends on the material. For a monatomic ideal gas, interestingly enough, we have a constant that only depends on whether it's monatomic or not. So any monatomic gas will have the same heat capacity at constant volume, 3/2 R, because R, of course, is the universal gas constant. Now, if you do a different process, and by the way, so constant volume, remember, work is 0 for constant volume processes. So from the first law, the heat is the change in internal energy. So the change in internal energy is also NCV delta T here. Okay, so let's try the constant pressure process. So again, in general, this equation will apply to all ideal gases. Q is NCP delta T. Okay, so up to there, it's a general equation. Cp is the heat capacity at constant pressure. Now for a monatomic ideal gas, we have shown previously that the heat required to change the temperature is 5/2 nR delta T. So again, we compare these two versions of the equations, NCP delta T and N 5/2 R delta T, and we find that the heat capacity at constant pressure is 5/2 R. And again, so that is a result that's true for a monatomic ideal gas. But again, it doesn't depend on the type of monatomic ideal gas. Any monatomic ideal gas has this value for the heat capacity at constant pressure. And if we go back and think about the first law again, so we see that Q is W plus change in internal energy. So the reason this Q, the constant pressure Q, is larger than the constant volume Q is because of the work that's being done here. Now, interestingly enough, we remember that the change in internal energy does not depend on the process. It only depends on the initial state and the final state. So it really actually depends on the temperature difference between the two states. So even though the change in internal energy has this equation NCV delta T that looks like it only works for constant volume processes, it actually is a general result. Okay, the change in internal energy is NCV delta T can be applied to all processes because it only depends on delta T, the change in internal energy. Okay, work, of course, is process dependent, and because of that, Q, heat, is also process dependent. But the change in internal energy is not dependent on the process that takes you from one state to another. Okay? And you can apply NCV delta T to any process to find the change in internal energy. Another general result here is that Cp is Cv plus R. That's certainly true for the monatomic ideal gas. Cv is 3/2 R. Add another R, which is 2 over 2R, and you get to 5 over 2R, and that's what Cp is. And that's true in general. So there's an equivalent relationship for diatomic ideal gases and polyatomic ideal gases. Okay, so there is heat capacity, and there is this interesting result here that change in internal energy, in general, can be given by NCV delta T, with appropriate values of Cv depending on whether the ideal gas is monatomic, diatomic, whatever. And even though it looks like it applies to constant volume only, you can apply it to all processes because the change in internal energy is process independent. Okay, so now we'll switch over to our example problem, and here it is. So we have a container of monatomic ideal gas. We choose the number of moles so that N times R is a nice round number. N times R is 20 joules per Kelvin. And we start with the gas in state 1, and the pressure in state 1 is 20 kilopascals. And the volume in state 1 is 100 times 10 to the minus 3 cubic meters. That's also 100 liters. So we want to know what's the temperature of the gas in state 1, T1. So we know N times R, we know P, we know V. So we're looking for T, so the obvious thing to do is use the ideal gas law. Okay? So that's one thing to remember about thermodynamics is you've got all sorts of equations, including the first law and the fact that work is the area under the curve, and the change in internal energy is NCV delta T. But you also got the ideal gas law that can tell you a lot. So in our case, remember PV is nRT, so we solve for T. T is PV over nR. In this case, PV is 2,000 joules, kilopascals times meter cubed. The kilo, the 1,000 in the kilo, is canceled by the 10 to the minus 3 in our volume. And we divide that by nR, 20 joules per Kelvin, and we get 100 Kelvin. And again, here's a reminder that the factor of 1,000 in the kilopascal cancels the 10 to the minus 3 in the volume. Okay, so now we're going to add some heat to this gas. We're going to add 2,500 joules of heat. And we're going to do a constant pressure expansion. And the gas reaches a new state, state 2. We want to know the final temperature. Okay, so let's see how we might approach this. So we know that at constant pressure for monatomic ideal gas, well, first of all, we have the first law. Q is change in internal energy plus W. That's a general statement. Now for monatomic ideal gas, the change in internal energy is 3/2 nR delta T. That's consistent with NCV delta T, where Cv is 3/2 R for monatomic ideal gas. And then the work done is P delta V for constant pressure process, but because the ideal gas law, P delta V is the same as nR delta T. So we can replace the work by nR delta T. Okay, so here's our 5/2 nR delta T that we've seen before, the Q for a constant pressure process. Okay, so we know nR, we know Q, we know what 5/2 is, so we can find delta T. So delta T is 2/5 of Q over nR. Q is 2,500, so 2/5 of 2,500 is 1,000 joules, and nR again is 20 joules per Kelvin. So we divide 1,000 joules by 20 joules per Kelvin, we get 50 Kelvin. So that's the change in temperature. Of course, the temperature is going up here because the heat was added here. And so our initial temperature was 100 Kelvin. We've just added to that 50 Kelvin. So now we're up to 150 Kelvin. So how much work was done by the gas? So we had 2,500 joules worth of heat. Part of that went to the change in internal energy, and the rest of it went to the work. So how do we attack that? So we go back and deal with the work part. We've already seen this on the previous screen. Work is P delta V, which is nR delta T. And so that's 1,000 out of the 2,500 joules was the work. And of course the rest went into changing the internal energy, the other 1,500. And don't forget that this equation, work is P delta V, which is equal to nR delta T. We can only get away with that for a constant pressure process. Okay? And more generally, we have to go with the area under the curve. And if pressure and volume are both changing, then you can't just go with nR delta T on the other side. Okay? It's only because one of those things on the left changes that we can simplify it to nR delta T. Okay, last question about this. What's the new volume? And so let's see, you can probably do this in your head. Pressure stayed the same. Temperature went up by 50%, so the volume should go up by 50% as well. Okay, so we can use the ideal gas law to calculate that if we want, just to check it. So arranging the ideal gas law to solve for volume, volume is nRT over P. nR is 20 joules per Kelvin, T is 150 Kelvin, P is 20 kilopascals. Of course the pressure stayed the same, so P2 is the same as P1. And so you do the math there and you do get 50% a larger volume than what you started with, 150 times 10 to the minus 3 cubic meters. Okay, so there's an example of how we put a lot of things together here. Expressions for changing internal energy, doing the work, first law of thermodynamics, and also the ideal gas law. Bring those all together into one example. Okay, so that is all for today.